Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at advanced mechanics for HSC physics, and we are covering inquiry question 3, motion in gravitational fields. So what our lesson goal is today, or the lesson title, is launching into and orbiting space. So we're going to actually try and derive a mathematical relationship between escape velocity and conservation of energy, but we're also going to try and use our formulas from orbital velocity and look at some differences between low Earth orbits and geostationary orbits, and also looking into how they are used because of it. Okay, just before we begin, let's have a look at some multiple choice questions. We have a satellite orbiting Earth with an elliptical orbit, as you can see like so, passes through positions X and Y. Which of the following table correctly identifies the position at which the satellite has a greater kinetic energy and the position where it has a greater potential energy? Okay, pause it here if you want to have a go. I'll go through the answers. The answer is B. So at position X here, there's a greater kinetic energy, and position Y here, there is a greater potential energy. Okay, so that's what we have there. Question B, a satellite initially in a low Earth orbit is moved to a new orbit where its gravitational potential energy is half its initial value. What is the gravitational force experienced by the satellite in its new orbit? Is it half the amount of force, twice the amount of force, 4 times, or a quarter? Okay, so the answer here is D. I'll quickly explain why that's the case. So this is our gravitational force, gmm over r squared. Now, assuming that this is a constant, we can rewrite this as a 1, arbitrary number. Okay, if we increase our if the gravitational energy has halved, meaning by this is gmm minus, so for it to halve, that means your distance would need to have increased by 2. So for our radius here, 2 square would give us a quarter. So we have a quarter of the initial force. Okay, so we talked about initially orbital velocity and how to derive it. So the assumptions that we tend to make is the orbit is relatively circular, and so if that's the case, we can place centripetal force and gravitational force to be equal to each other. We get the following formula, and then we can derive a formula for orbital velocity. So that's what we can find here. We see that the orbital velocity is gm over r, obviously rooted like that. Okay, so we'll go to our first point of this lesson, and that's to look at the types of applications of near-Earth orbits and geostationary orbits, and try and relate them to their uses. Note here we are looking at satellites. Now, satellites could mean anything that orbits around another larger object. So our moon would be a natural satellite, and then the kind of satellites like the International Space Station, we call those artificial satellites. So two common types that we can look at is a low Earth orbit that orbits at about 300 kilometers above the surface of the Earth. And we can also look at a geostationary orbit, which is about 36,000 kilometers above Earth. So based on their distance away from the surface of the Earth, there'll be two things that we can actually look into. And we can actually express that by using this formula here. The altitude is only 300 kilometers. compared to 3,600, which means that for low Earth orbit, the distance in separation from the Earth's surface is rather low, so that's small. As a consequence, the orbital speed will be very fast, because as you can see, orbital velocity is inversely proportional to the orbit distance. Contrary, a geostationary model or geostationary Earth orbit, because it has a much higher separation from the center of the planet, it will have a smaller velocity. Okay, so let's try and work that out as some calculations. So using our formula of orbital velocity, let's try and work out what the orbital speed of a low Earth orbit is compared to a geostationary orbit. So if we look at a low Earth orbit option, just do our calculations. Our data is given to us, or you can use your data sheet. So, and then convert that into meters. Okay, we'll find that the orbital velocity of a low Earth orbit is about 7,720 meters per second. Kind of ran out of space there. I should have given myself a bit more space. And then for a geostationary orbit, so G for geo, 6.67, 10 to the power minus 11, mass of Earth, and also, whoops, I forgot to add the radius of the Earth. Okay, so don't forget to add the radius of the Earth because it is orbiting around it. And then for our geostationary model or geostationary orbit, we get a speed of about 3,065 meters per second. So you can see there is a big contrast in terms of the speed. Our low Earth orbit is almost twice the amount of speed as it is for the geostationary model. Okay, so we've talked about the speed. Let's talk about the orbital period. Now, when we talk about orbital period, we can use the relationship of Kepler's third law. We know that the period squared is directly proportional to r squared, or the orbital, average orbital radius. So if the orbital radius of the low Earth orbit is smaller than our geostationary Earth orbit, then we also expect the time it takes for it to rotate once around Earth will be shorter. And that makes sense too, because if we're traveling at a faster velocity, tangentially speaking, the time it takes for it to rotate should also be shorter. So for our geostationary orbit, because it has a larger radius, it would also have a longer period for that one rotation. Okay, so question 2. Now try and calculate what the difference in the periods of the two orbits would be. Okay, this time hopefully I'll have enough space for myself. So set out your equation. We are using Kepler's third law of planetary motion, and you can write it like so. Okay. If I rearrange my equation, it'll look like this. Okay, r cubed is obviously the distances. 4 pi squared is a constant, g is a constant, m is the mass of Earth. So let's go for the low Earth orbit, or LEO. So we have the orbital radius plus the actual altitude in which the low Earth orbit is in, times 4 pi square divided by the gravitational constant times the mass of Earth. And what we're left with is about 5,000, or approximately 5,425 seconds, which equates to about 90.4 minutes. So it takes 90 minutes for a low Earth orbit to make one full rotation around the planet. So that's pretty fast. If we look at our geo orbit or geostationary orbit, again, write in your substituted values. Okay, remember to convert the kilometers into meters. And now constants will stay the same for this one. And so we get a time of about 86,843 seconds, which equates to almost 24 hours, or just above 24 hours. Okay. So one is 90 minutes for one rotation, or one orbit around our planet. The other takes about 24 hours to do that one rotation. Okay, so let's actually look at the different types of orbits. So the one we're talking about was the low Earth orbit. There are different types, and the geostationary orbit. So we can look at different types of Earth orbits by incline. So how they, the kind of angle they have compared to, you know, the equator or maybe to the poles. Okay, and then obviously you have an incline angle like that. Now, generally speaking, if you want to sort of survey the different types of climates on Earth, then you would try and use a polar orbit, because if you actually have a look here, you have the North Pole, you go into the northern tropics, and then you go to the southern tropics, and then you go to the South Pole. So if you want to, you know, survey all the different types of climates, you might want to do a polar orbit. If you want to just, you know, look at the general climate of a specific region, then you might want to look at an equatorial orbit. Sometimes you might want to do an inclined orbit. That again I would assume uses similar parts. So to cover a range of latitudes from the northern and southern hemisphere, whilst the polar orbit can give you a full coverage. Okay. The ones that we looked at so far were the orbits by altitude. These ones, more in terms of functions, they're not so much in terms of what we can explain with the physics. This is more, you know, based on the purpose you want to achieve with it. But if we're talking about the physics of it, we have the low Earth orbits. You can do it really quickly, or you have the geostationary orbit. Now, as we talked about, a geostationary orbit takes 24 hours to do one rotation. That's the same amount of time the Earth rotates once, or revolves around its own axis once. So the benefit of these two models, let's quickly have a look. So for the low Earth orbit, the reason why you want to, you know, manufacture these is, firstly, it's less expensive and it requires a lower signal strength. Because it's closer towards the Earth, the signal used doesn't need to be as strong. You can take satellite images. So as we said again, a low Earth orbit will probably tend to be used for surveying the land and trying to look at different landscapes around our planet. So it's because it has a higher resolution because of a low orbit. These orbits can take a particular pathway, like we said. It could be equatorial, it could be polar, it could be incline. And then we also have, usually for surveillance purposes or spying, the reason being is it has a shorter time period for one revolution or one orbit, meaning by you can track changes in the landscape a lot faster. While as a geostationary orbit, it usually just travels directly above the equator, so an equatorial orbit. It occupies the same position in space above Earth, meaning by if it's above Australia, it will continue to rotate around the planet, but it will always be above Australia because we are rotating at the same speed, effectively. Okay? It's used for communication and weather satellites, which makes sense because if your satellite is stationed in the same position for a continuous period of time, then obviously you can actually track how the weather is changing. Okay, antennas on Earth can be fixed to always stay pointed towards the satellite without moving. So it allows for flexibility as well. Okay, so the second part of this lesson, we're going to be looking into, again, looking back at Kepler's law of planetary motion, but since we've been focusing on circular orbits, we're going to also look at non-circular orbits, and we're going to try and see what changes to the total energy of the system is, depending on if the orbit is going circular or maybe if it's in an eclipse, because that's an eclipse would be non-circular motion. Okay. Whilst we're going through that, we're going to also just quickly go through what the effects of centripetal acceleration, orbital radius, and period and velocity would have on the rotating object. So let's have a look. So, quick note, total energy, a common name people use is mechanical energy, and that is just the addition of the potential energy and kinetic energy of the object. Now, if we're talking about a satellite in space, we're looking at gravitational potential, and we're also looking at kinetic energy. Okay, so we have GPE plus KE. That is the kind of note of our total energy. We've also talked about what the formulas are. So gravitational potential is a negative mgr. Kinetic energy is half of it, but in the opposite component, so it'll be mg or gmm 2r, and then total energy is just half of our gravitational potential, so written like that. So what we can say here is the green line, that's our kinetic energy of our rotating orbit. This red line here is our gravitational potential, and this purple line is our energy total. You can see here that the centripetal force is constant because we have a uniform circular motion. All right. We can also see that the centripetal acceleration again is constant, and also the orbital velocity is constant because we have a perfect circular motion. So under these circumstances, the kinetic energy does not change because v has not changed. The radius has not changed. And as a consequence also, because there's no change in the radius, then obviously the centripetal force and acceleration would stay the same. Okay. What we're going to look at next, if we just do a quick comparison. So in that simulation you saw in a circular orbit, we were saying that the Earth was rotating around the Sun at about 300,000 meters, or not 300,000, 30,000 meters per second. We're going to then look at two other orbits, both elliptical, but one where the velocity is less than 300,000, so 24,000 meters per second, and one that is much faster at 45,000 meters per second. So what we have here, if we're slower than the circular orbit, we'll find that, as we talked about here, the gravitational potential here is at its maximum. The kinetic energy in this position is at its maximum here. Now there's actually some terms that we can actually use to describe these 2 points. Okay, so if you have a look at here, the pedigree in a elliptical orbit, that's the point where the eclipse, where the velocity is at its fastest point, and the radius is at its closest point. So, as we know, if radius is directly proportional to the time period, that means if the radius is at its smallest point, the time period is also at its smallest point. If we look at our equation, v equals 2 pi r over t, then, we have maximum velocity. As a consequence as well, because r is at its smallest, our gravitational potential is at its smallest, and our kinetic energy is at its largest, based on the formulas that we have. So remember, kinetic energy is gmm2r. So if this gets smaller, okay, as this decreases, this will increase, while as gravitational potential energy, the formula for this is a negative value. So if I'm decreasing r, I become less negative, so I'm getting closer to 0. Okay, so or actually I'm going away from 0. Wait, sorry, so if I get as r decreases, then our value would become smaller. Okay, so it becomes more negative, so to speak. Whilst if we add the apogee, I think I said that right, the point on the eclipse where the velocity of the object is slowest, as you can see. So if the radial difference is at its maximum, according to our formula here, when this is at its largest point here, the time period is also at its largest point as well. As a consequence, if it takes longer to rotate, that means our velocity will be smaller here compared to here. We also know that as r is very big, okay, we are approaching closer to 0, so we'll have a higher gravitational potential here compared to here, because if we're closer, the gravitational potential becomes smaller. And as a consequence, because of conservation of energy, kinetic energy will obviously decrease. But let's go back to our simulation and actually compare the two orbits, or the two elliptical orbits. Okay, so I'm going to show you the orbit of the 24,000 meter per second change. It'll take a while. Okay, so now that you've seen the full rotation, let's quickly talk about what's happening. You can see as we get closer towards the sun, our radius is decreasing, our centripetal force and acceleration is increasing. As a consequence, as that, we are moving faster at this point here. As we go further away, the centripetal force gets smaller, so our velocity is getting smaller, as you can see here. So that is changing our kinetic energy. Now, as we get closer again, you can see not only is this acceleration getting larger, our velocity is getting larger, and we see that exponential increase again. And what you can see is with our potential energy, it is doing the exact opposite of what our kinetic energy is doing. However, at no point does our total energy actually fluctuate, which makes sense because we're saying this is the law of conservation of energy. They should stay the same at the end of everything we're doing now. So that's great, it's consistent. Now let's look at if the object was moving faster than 300,000 meters per second. So let's say we're moving about 45,000 meters per second. Let's have a look at what this orbit would look like. Okay, I'm going to pause it there because spoiler alert, the planet doesn't actually come back anymore. So I'm going to just reset it and I'll explain what we're seeing. So we start from this point here. As the velocity of the planet is quite large, it breaks the orbital that we're seeing here. And as you can see, as it goes further and further away, the centripetal acceleration is getting smaller and smaller and smaller. Since it's getting smaller, then less likely our planet can be drawn back in to the center of the sun here. As we go further away, obviously the velocity will begin to decrease, and that is seen as a decrease with our kinetic energy. That's consistent with what we saw before. We said that when it gets the closest point is where it has the maximum kinetic energy, and as we're going further and further away, that energy begins to decrease further and further. Now, obviously, because of the way the formula is structured, as we go further or as R increases, the kinetic energy will get closer and closer to zero, so will the gravitational potential, but unless they're at infinity, then obviously they won't reach zero. You can see that in this location, the maximum or the total energy is zero because the kinetic energy and the gravitational potential essentially cancel each other out. Okay, so we've covered quite a few things today. We've actually talked about orbital velocity, the different types of orbits that we can achieve, and also what we can see when planets are going in different types of orbits, circular and non-circular. In our next lesson, we're going to look into escape velocity and how to change the motion of a satellite from one position to another. But as always, thank you for listening, and I'll see you next time. Like and subscribe if you haven't done so already.